as you heard, Louis created an incredible environment in his group. And it was clear that there were going to be big discoveries. He had a dedicated staff of physicists, and some of them, you've seen them here. Exceptional graduate students, one of which is Stan Wiki, who was going to be our closing talk. And then he had an army of very talented engineers, programmers, and a greater even army of scanners working 24/7. As you heard, they couldn't get up from a chair unless someone else would take the chair. That's how the 1 million event a year was achieved. And of course, the commander-in-chief encouraged everyone to try new ideas, to do new things, and go beyond what you think your limitations are. You heard a lot of this, but I will now explain why he won a Nobel Prize, in other words. What you see here are 6 cubes. And these are what we call, what do we hear? This thing is not really working the way I thought. Oh, okay. So how do I get rid of this? Huh? Yeah, but I want to get rid of this. So, this, where is the laser? Yeah, thank you. Yeah, right. So these cubes here, you see, are what we call the building blocks of matter today, in the sense that we can explain all those particles that Philippe was talking about by using these basic blocks called the quarks. And Louis really had to do with the first, with UDS, and the other 3 came later, and as we'll see. Okay, it doesn't go down. Arrow? The arrow doesn't seem to work here. It's supposed to be the arrow?
Yeah, just the arrow.
It doesn't work. I guess I have to use the mouse. So where is Ben? There we are. Okay. No, it up and down didn't work. Okay, so here are the events that you saw. It was one of the events you saw. And you have here in this case, you see that there are 2 of these V's that you saw, the lambdas. And this event is P bar, lambda bar. So these are the 2 V's here. And there is a gap between the end of the antiproton and those 2 called the lambda bar. Greek letters were used for new particles as they were found. And now the programs that Art talked about were able to reconstruct exactly what happened here, which is have all the energy and momentum conservation, and you would at the end know everything about this particle that you did. Yeah. So now comes the first discoveries in 1999. And the Stanwachiki, as you see here, there is the names are not on this plot. Okay, you see, this is the film that the scanners had. As you can see, it's very hard to see anything in here. And I believe Bonnie Glaser was the one who found this. Bonnie here? Okay, yeah. So you see here, they saw a V, kind of in this place. And then there is another one out here. And there is the end of the K minus that comes in. So it looks very complicated, but because of all these programs that were written and the ability of the scanners who found it and so on, turned out that this was a particle which had never been seen. It's called Xi0. And as you can see, this was immediately out in the New York Times. And the top it will say, 6 scientists trapped new particle of atoms after 70,000 photos. So this was the very first very exciting discovery. And it was, of course, predicted by theorists, so that made even, more relevant because that has something to do with the building of the quark model that we will see. So what particles were known in 1957 when the bubble chamber started operating? So there were the protons, and in the nucleus, we knew about the nucleus. The atom here is, of course, proton and neutrons are part of the nucleus, and then the electrons. And then there are the leptons. And now the protons were called baryons, because they were heavy compared to some of the other particles which were known, like the leptons, the electrons, the muons, and the neutrino. And then there were other particles like mesons called, like the pion and the kaons. We've seen those in the pictures. And the kaons had the property which was called strangeness. They were strange because, in fact, so they were heavy, like the K, the kappa, the kaon. But they lived for a while, and then they kind of decayed. So they were away, we were seen moving through the bubble chamber and then decaying to something else. And the baryons, of course, the lambdas and the sigmas also were strange, and the proton that we know about, and the xi's. So these were particles which were known, and the property called strangeness was when you produce two particles, they have to have the total at the end, the strangeness at the end should be the same as at the beginning. So you had like 2 produced a K plus and a sigma minus, so the total strangeness at the end would be 0. Now, here is an artist's view of what was going on in that period, 55 to 64. This is a brief history of particle physics in brush strokes by Gerson Goldhaber, our friend and colleague, who was putting down on canvas what was going on. So in the Bevatron had started operating in around 55, I believe, and there was this big discovery at the time of the antiparticles. So the proton and the neutron, and the antiproton was the big discovery, which led to a Nobel Prize in physics from LBL, one of the many, and of course the antineutron. But then later, 64, which is essentially the bubble chamber results, and you see here all these particles floating, Y star and so on, we'll see about them, but these were discovered all in bubble chamber. And I guess Gerson was put the one that he discovered, which is here, George Trilling and Goldhaber discovered this one, which was also at the same time seen in the Alvarez group. And then he put in here this question of building blocks and how the particles can be put into grouped together somehow. So from the artist's view, then we move to what the situation was. Why it was necessary to have something like the quark model, because the particles that were growing as the time went by, and you see here that this is 1960, and by then there were pions and kaons, as I said earlier, lambdas, xi's, and this is the xi 0, but then they start coming faster and faster, and you know, I'm filling our tables that Arthur talked about. That table kept being filled continuously by new and new particles. And in fact, 18 more particles were discovered, mostly in bubble chamber, because Louis was distributing the film that he got in many, many other places, like UCLA, and Johns Hopkins, and so on. So more than just the LBL group was working on that film. And so there are 18 which have been discovered in the chambers, and that was essentially motivation for the Nobel Prize. Now, some of these particles are called resonances. Why they're called resonances is because they decay very, very fast. For the lambda, for example, you saw that it was away from where the interactions happen. But for these particles, you don't see them moving away from the interaction point because they live very, very short, like 10 to the minus 5 seconds. Okay, so here is the first one of these resonances found here, 13 sigma 1385. This found, you have all these wonderful programs which were discussed before, reconstruct the whole event like having a lambda and 2 pions. So this is a K minus comes in, a beam of K minus, and this is the bubble chamber, the hydrogen. And you have 3 particles coming out. And what you see plotted here is the kinetic energy of one of the pions. And you see that there are many, many more here than elsewhere. And so this is called a bump. And in this particular case, we are showing the other pion here. And this is called a Dalitz plot. Dalitz was a theorist from Oxford who was spending time here at Berkeley at the time, since it was the center of particle physics at the time. And so this was his idea of looking at events in this way. And of course, Louis, in his book, actually in his Nobel lecture, credits Bill Gargiano and Stan Wojcicki for having invented this technique, bump hunting. And by hunting for bumps, more and more resonances showed up. And here are some. Hit this one. Actually, Margaret, did you make it? Oh, there she is. She was the first author of many of the papers because we're in an alphabetic order, and also because she was doing a lot of work. And there are more bumps appear, and here is the 18 that I was talking about, of which some were done, discovered directly at LBL, some of the others were discovered from other institutions like UCLA, and others were co-discovered with CERN or Brookhaven and so on. So what we do with all these particles? It's the elements. The table of elements came up because it was impossible to understand what all these things were. And Mendeleev did that way back. And there were some theorists who said, well, we've got to find something by which we classify these particles. Instead of talking the individuals one, we can talk about a group of them which have the same properties. And that's how the eightfold way came up by Gell-Mann and Neyman independently. And where did the name eightfold way came? Well, Gell-Mann is reading a lot and knows a lot about everything. He's a very smart physicist, and somehow he took this eightfold way from the teaching of Buddha, who says that this is the appropriate way to reach nirvana. So, okay, that was the idea. And in fact, this idea of putting the particles together in group of 8 was the starting point for the quark model. And there was, in fact, a mathematical way to treat this, which was SU3, because you can make 8 particles to group together if you have basically 3 elements to start with, and these were the 3 quarks, the 3 building blocks. And this way, there might be a way of put some order in the so-called particle zoo. That was called at the time, particle zoo. Okay, so here is then, since I don't have a lot of time, I will try to be shorter now. So with this 3 by 3 bar, these measurements are made by a quark and an antiquark. And then you can look at 3 basic ones, 3 and 3 bar, a quark and antiquark, and then you produce an 8 and a 1. So here is this representation of this octet and singlet, and you have all of these particles which can be grouped together, being part of this JP equals 0 minus, which is another quantum number. So the nice thing about this also was that initially there were only 7. And where is the 8? You know, we need 8 really to complete this octet. And yeah, sure enough, the eta came up in 1961, was found. Here it is. And later on, the 9th, which is the 8 prime, was found in 64. Now, of course, here this is what they've done. And the pion is a U and a D bar, the K minus an S and a U bar, and so on. And then you have now another one of these octets for different quantum numbers, which is J equal 1. And the entire octet here, nonet, was discovered in Lewis bubble chamber. The K star that we saw earlier and then the rho, which was a co-discovery actually with some other group, and the omega was the one discovered here, and the phi also was a co-discover, but this all nonet was found in the group. Now with the baryons, the idea was that instead of three, they're done out to make out of 3 quarks. So here is a proton, there are 3 quarks in there. You can, then if you work this algebra, this SU3 algebra, you see that if you have 3 times 3 times 3, so you have all possible way of putting together 3 objects. You end up with a group with 10 and a group with 8 and another one with 8. And so you can just take care of all sorts of particles in there with just this simple idea of starting out with 3 quarks. And here is one with this octet, and this is the Xi 0, the first one that was discovered in the group. And here you can see what they are made of, how they group together. The one particle which is here is the omega minus, and I will show you the couplet, the 10, and you see that this is the Y star 1385 is here shown. Xi stars were also discovered, co-discovered in the Alvarez group, and the omega minus was missing. This, unfortunately, there wasn't enough energy at the Bevatron to find this one, so it was found at Brookhaven later on with a bigger chamber and higher energy. So, okay, this is the Nobel Prize motivation, and it says, for his decisive contributions to elementary particle physics, in particular the discovery of a large number of resonance states made possible through his development of the technique of using hydrogen bubble chamber and data analysis. So what happens today? Well, today there are 6 blocks. Some were discovered. The charm was discovered at SLAC Brookhaven 74, the bottom in 79 at BNL, Brookhaven, and the top at Fermilab in 1995. And of course, I was fortunate to be among the people who worked to find this last quark. There are today a total of about 340 particles. So, and it's good that somehow we can classify them. This is how those triangles and octagons and so on look today. This is only, uses here only 4 quarks are used to work, D, U, S, and C. So the chairman tells me that my time is off, but let me just say that, Louis has been always shining light, a person you could go to and discuss your problems. He would come and find out. When he stopped working in bubble chamber, he would come around and say, what are you doing, what are you up to, and what's going on. And here I'm coming back from SLAC, where I was working on an experiment, and he wanted to find out how things went and what the progress was, and so on and so on. So he was, always supportive of anything we do, and he would always encourage to go on farther than what we thought we would. And I had a story which I don't have time to tell, because the chairman tells me to go, but maybe I'll say it in private.